Bom dia. Para a nossa primeira palestra de hoje, a gente tem um convidado internacional, então nossa palestra será ministrada em inglês. Our lecture will be about advancing state estimation, insights from random finite sets, which will be presented by Professor Martin Adams, who teaches electrical engineering and is the former director of the Department of Electrical Engineering at the University of Chile, as well as being a main investigator in the industrially sponsored Advanced Mining Technology Center. He obtained his first degree in engineering science at the University of Oxford in 1988, followed by a DPhil from Oxford's Robotics Research Group in 1992. His career has spanned some of the world's leading research institutions, including the Swiss Federal Institute of Technology in Zurich, Nanyang Technological University in Singapore, and the European Semiconductor Equipment Center in Switzerland. His research focuses on autonomous robot navigation, sensing, sensor data interpretation and control, which are areas that connect deeply with today's topic. Please join me in welcoming Professor Martin Adams.
Okay now? 1, 2, 3? Everything good, yeah. Thanks also to Guilherme, who's done a lot of the organization, I think, to get me here. He's been back and forth with emails, which has been very helpful. And of course, Gabrielle coming all the way to the airport, picked me up, I think 7 hours in the car, probably, there and back. So I appreciate all your help, and it's really a great honor to be here today. So as you just heard, my name is Martin. I'm supposed to stay near the microphone, so I won't go walking around too much. I'm here from the University of Chile, Department of Electrical Engineering, and I'm also part of a center in Chile, because in Chile, mining seems to be the key industry, so it's called the Advanced Mining Technology Center, or AMTC for short. And I'd like to spend about the next 45 minutes, 50 minutes or so, talking about, as you just heard, advancing state estimation, insights from a mathematical tool or mathematical paradigm that we call random finite sets. The reason for these pictures is that within about the last 20 years, random finite sets have found applications in very, very diverse areas, some of which I'll talk about today. Those areas range from tracking junk in space with radar or with optical telescopes, to making maps in underground mines, as you can see on the bottom left. This is actually a picture within the Esmeralda mine, which is part of the El Teniente mines within Chile. Believe it or not, those mines have a length of 6,000 kilometers, 4,000 of which are actually still in use. So mining is a very big industry in Chile. Also has applications in monitoring and tracking people for security, making sure that the right people are in the right places, and applications as diverse as tracking, monitoring, the lineage, and also the number of cancer cells under a microscope. And you can see some examples later for applications in breast cancer. Okay, I believe I can use this one. Very good. So I'd like to split the presentation into the following 4 points. Firstly, I'm going to spend a bit of time, maybe the first 15 minutes or so, talking about the applications that we're involved in, to try and give you a little bit of some scope of why we think random finite sets are useful, or at least what they're used for. In part 2, I'll focus on why the random finite sets, in particular, what is the motivation for coming up with new tools to do state estimation. And I'll try and make some comparisons and sell to you or convince you why they're actually becoming very useful and being used in a lot of diverse areas. In the third part of the talk, I'm going to focus on a particular application that I've been involved with for many years, all the time since my PhD, basically, and that is the simultaneous localization and mapping problem, as well as multi-target tracking, which are two very closely related areas. So I'll be talking about SLAM and MTT, and again, going into a little bit more depth of how we solve those and make some comparisons. And finally, I'll wrap up the presentation with a little bit of some presentation on what I think is the future in these areas. So, applications of random finite sets. As I mentioned, when you go to Chile, it's the #1 industry there is mining. There are many small industries that are also set up, but they're related to service technologies within the mining industry. This is a photo taken within the El Teniente mine, the one I just told you about. And when you enter there, it really is like going into a city. There's traffic lights inside the mine. You have to wait sometimes significant periods of time for other traffic to move around. And this is a picture of an autonomous shovel loader. So pretty dangerous vehicle, because as you can see, it's very big. And they call it autonomous because they buy the shovel loader, and then companies such as Sandvik, which is a Finnish company, they come and put sensors all around vehicles like this, and they effectively teach it how to drive autonomously within the mine. So to say autonomous is actually a bit ambitious, because they're still quite naive in some sense. If unexpected situations arrive, then they just stop and wait to be rescued. So people still have to go in and rescue them sometimes. But the idea is that initially a driver would take this at certain locations, and then the autonomous system can repeat what the driver has done based on the sensor information that it gets as it's moving. This is some of the students, some of our research students. This is probably about 10 years ago now. We were invited to take part in some mapping work within the El Teniente, or within the Esmeralda mine, which is part of that network. You might say, why do we want to make maps in mines? Surprisingly, mines change shape a lot of the time because they're being excavated, materials are being taken out. And you might be amazed that in places like Pennsylvania in the United States, the mines are so old, they sometimes do not know exactly underground where they are. So for example, when they're doing construction above the ground, they're not exactly sure whether they are building on top of disused mines or not. Once you go underground, of course, GPS doesn't work. So they need to have methods to accurately find out where these mines, where the locations are. This is an experiment we did with a vehicle that you can see here called the ClearPath Husky robot. And we've got various sensors attached to it. There's a millimeter wave radar, the one that looks like a very strange coffee machine, if you like, at the top there, with a rotating swash plate. We've got a laser rangefinder, and we were there to actually make some maps and even do volumetric measurements. Sometimes mining companies in Chile will pay quite large amounts of money for companies simply to come and measure the volume of a section of the mine, because they need to know how much they can excavate, and also sometimes the surface profile in order to be able to excavate materials as precisely as possible. Here you can see a video, if you like, some of the work we did there. This is something we did some time ago. This appears a little bit like a movie in the top left-hand corner, if you like, but the important thing is that every one of these white points you see in the top left has geometric meaning. Because it's been recorded with a 3D laser rangefinder, they all have X, Y, Z coordinates, and that allows us to really make geometric maps to know precisely the shape of parts of the mind. We can calculate volumes. And those colored points you see there, although they don't look very related to the mind topology, are actually from the radar that's on board. Because sometimes when there's high levels of dust, we actually need the radar to help us register the LiDAR or laser detection and ranging data correctly. So the challenge here is, if you like, is we were doing just stop-start maneuvers. So the vehicle would stop, take scans, we would move again. And in this particular example, we did 45 individual scans that are shown in the different colors at the bottom there. Examples of individual scans are the ones at the top. And of course, the challenge is to register those correctly or stitch them together correctly to get a correct and meaningful map of the environment. So this is then a plan view of that part of the mind that we actually moved around. And again, we're using these random set technologies that I'm going to talk about later to try to improve the registration process, specifically when we have misdetections, false alarms, and spatial uncertainty that I'll mention later on. Completely different application that I mentioned earlier is tracking cells under a microscope. On the right is the result of a time-lapse video. So if we have, you imagine a camera looking into a microscope, it's recording for a period of time. And the idea is to be able to identify, track cancer cells, breast cancer cells in this case, under the microscope. And importantly, medics want to know what we call the lineage. How did they originate? Cancer cells obviously split, they spawn, and they become multiple cells. And some of the challenges in doing that is, if you look a little bit here, the form or the shape of the cells changes significantly before they split, a process we call mitosis. So the cells are in the process here of splitting into different cells, and image processing algorithms, it becomes quite difficult to actually detect when they're about to split so that we can initiate new tracks. So again, part of the challenge in this work has been dealing with the fact that image processing algorithms sometimes miss the particular time when they're going to split, and being able to optimize things so that we can get the best tracking data possible. On the right here, then, you see track labels identified with colors. That means each individual color is supposed to represent a unique cancer cell which is moving around under that microscope. And the challenges that we have is being able to monitor, we're calling it cardinality, that corresponds to the number of cells being estimated as time goes on through that time-lapse video. Here we're seeing the number of splits, or the number of spawns, if you like, mitosis we call it. So at each time increment, how many cells are splitting into different cells. Again, another very, very different application, but again, mathematically quite closely related to what I was just talking about, is that of the posh name is space situational awareness. That's the very fancy name. The real thing we're trying to do is to track junk in space. It turns out, as you can imagine, there are so many satellites now in space, thousands from Starlink actually, but even broken or defunct satellites that are moving around the Earth at very high speeds. And it's actually becoming quite dangerous to launch from the Earth. So we have to avoid collisions at all costs. The reasons we need to avoid collisions is because sometimes just small pieces of satellites, which are no longer functioning and have broken out, are typically going at about 15 times the speed of a bullet. And if that collides with any spacecraft, it can be completely destroyed. And those of you that have maybe watched the movie Gravity can realize it starts off a chain reaction. So it destroys a satellite or destroys some kind of a rocket, and that then splits into thousands of pieces, and they then start destroying materials as well. Here you can see a radar dish. This is in the south of the UK, so it's located around about that point down here, which was initially designed for weather monitoring, but since 2010 has been specifically used for monitoring space junk and trying to improve the catalogues of where space junk is. It turns out if you go to the internet, there is a website that you and I can access called 2 Line Elements, The reason it's called two-line elements, there are two lines for each satellite of data. And you can even give the name of a particular satellite, such as even the space station, the International Space Station is in there. Many satellites are in there. This one was the ETH II, for example, making a pass. And it will tell you where that satellite is supposed to be or is at a certain time. So I can give the time now and it will tell me where above the Earth's surface it is. The thing is, those catalogs are inaccurate for satellites which are no longer working. So satellites which are no longer working are no longer controllable, but they're still in orbit. And it's necessary for us to be able to update those catalogs. And some of the aim of this work, this one's sponsored by the US Air Force, is to be able to accurately improve these catalogs, even using amateur telescopic equipment, so anybody can contribute to the information. What you can see here is the result of a scan, a single scan from this radar dish. And all of these white points correspond to what the radar thinks are detections. So the radar says there is something here, there is something here. And there are even these bands where this particular radar actually fails to give information because of the hardware that's involved. I think it's quite easy for you and I to see that we arranged this scan as a satellite was passing over. You can see in this line. But importantly, what you see here is sometimes the satellite is detected, which was the ETH II satellite in this case, which is actually a broken one. It's something that is no longer controllable. Sometimes it was detected along these lines, but sometimes it's missed, particularly in the regions here and even in here. Also, of course, we're getting many, many false alarms. In other words, the radar says there's a satellite here, here where these white dots are, when in fact there was nothing there at all. So the challenge of multi-target tracking is to be able to, of course, identify the correct track and remove all the noisy data, all the interference. That same information, you can see it, the results of a simple random finite set based filter here. That same data I just showed you, at any instant in time, as the scan is being made, these red crosses correspond to detections, which are typically false alarms due to interference and weather. And the tracker has to then pick out the correct track or the correct satellite as it's moving over the surface of the Earth. Here you can see it's going slightly off course because of a lack of information. And then the blue arrow kind of corrected as it was maintaining that track. Now, for you and I, it's quite easy to see that there is pretty good data here, and we don't get so many false alarms. But we can actually improve target tracking by doing something called robust filtering, which means we're at the same time as estimating this path, which is the important part, that's what we really want, we estimate these parameters too. And these two parameters are very important. The first one is called the probability of detection. That is the probability of even detecting the target, which you could see was very low in some parts of the path. That corresponds to over here. And if we can estimate that at the same time as estimating the track, we can actually improve our overall tracking performance. Similarly is another one called the clutter rate. That's here. That corresponds to the number of false detections we expect per unit volume. So number of false alarms per meter cubed in space that we expect. And if the filter knows these parameters, it performs a lot better. Typically, though, we don't know how to tune them. So this is a robust filter that concurrently estimates those two things at the same time as estimating the trajectory. Some of the newer work we've done with space debris tracking has involved the use of optical telescopes rather than radio telescopes. And we're lucky enough to get information from a network of telescopes called the Falcon Telescope Network. That's the FTN, Falcon Telescope Network. There are 12 telescopes located all over the world. There's one quite near us in Santiago in Chile. There's several near Colorado, near the US Air Force Academy in the States. There's one in Germany, two in Australia. And the idea of this network is that at any time during the day, there will always be sufficient number of telescopes that are in nighttime so that we can actually monitor satellites as they're going by. Here we see geosynchronous paths of satellites. Most satellites are above the equator because they're in geostationary orbit. They have to be above the equator to be in a geostationary orbit. There's a lot of satellites in that band, very packed. But also we can monitor satellites which are in low Earth orbit, which are taking different trajectories. How do we do that with a telescope? How do we firstly even get measurements? Well, one way to do it, one of the most basic ways, is to look at what we call streaks. These are streaks in the satellite, and this data was given to us by the MITRE Corporation in the States. And images are typically very noisy, as you can see here. And there are stars that we expect to see in our telescopic image. There's a lot of noise because these are operating at very, very low light levels. And the satellite itself, or the piece of junk, if it's in low Earth orbit or even geostationary, we can expect it to create a streak in the image. Even in geostationary orbit, satellites make a figure-8 pattern as they move around, so it's possible to detect them. So if you like, as observations, what we typically do is we measure these streaks, so we're able to get the beginning and end of the streak and use that as a measurement. The challenge then in multi-target tracking is that we're not going to see that satellite probably for even up to an hour until the next telescope sees it. So we might get a streak or an observation for 12 to 20 seconds, and then we don't see it for several minutes, even an hour is possible, before we observe it again. So we need very good predictive models of how this thing's moving. Now, this is the one video I can never get to work in my presentation, so I've got it here. I'll start it separately. Here you can see the concept, if you like. So what we have here is, I'm not showing the Earth, but this is the center of the Earth, and these golden stars are locations of telescopes. And these streaks, they show the instantaneous measurements we're getting from these 12 telescopes. So we've got this network of telescopes around the world. They detect streaks, and what you'll notice is these pink crosses are initiations of tracks, and the blue circles are then confirmed tracks. So we're confirming that we've detected a couple of satellites, whether they're broken or not, I don't know, but a couple of satellites, now it's 3, moving around the world. And if you watch carefully, you'll start to see that the pink centers of these circles will start to spread as we keep predicting where they are. Maybe I'll wind it forward a little bit and you'll see it, I think, more clearly. Let's go forward. Yeah, here you can see, for example, the uncertainty in the location of that particular satellite is spreading. We're using orbital information so that it spreads in a Riemannian manifold, I'll talk about in a little while, not in a Cartesian one. And eventually, if that gets detected again, it's only once we get a detection or a streak corresponding to that that we can actually shrink that uncertainty. So you see that it soon becomes quite large, the uncertainty as it's going out. Now it shrunk because we got an observation from it. So the challenges here, particularly in space observations, is to have good predictive models on how we can actually update and monitor the junk as it goes around. Now, one of the problems with this method is that we're using what we call particles to represent the uncertainty. So samples from a distribution to represent where those things are. And those, unfortunately, are computationally expensive to run. So some of our more recent work, if I can just start this, has focused instead on using Riemannian geometry. So we have particles here on the left representing the uncertainty. Those are expensive because you need many particles. If I use a standard Gaussian to represent that, you can see quite how inaccurate it is. And we need Gaussians if we want to keep the computational complexity low. That allows us to then use standard filters like the unscented Kalman filter or various Bayesian type filters. On the other hand, if we can transform the whole process, instead of into Cartesian coordinates, we use what we call Riemannian geometry. We can actually create banana-shaped Gaussians. And if you think about it, an orbit should be banana-shaped because they're constrained to going around the Earth. So again, the concept then becomes something like this. You can see the filters initializing here. Uncertainty starts to spread in using Riemannian geometry. So it's creating this banana-shaped ellipse, if you like. And here we're kind of simulating measurements we're getting these streaks, and then we can once again shrink the uncertainty in the location of those satellites. Okay, obviously also this has applications in autonomous robotics. Here you can see one of our vehicles. It's a skid steer vehicle that we took into the mine, taken some time ago. These sensors are quite old now. It's just a 2D scanning radar, but we were able to do quite a few SLAM experiments with this actually in one of the parks near us, also to do some multi-target tracking experiments. So it's carrying a millimeter wave radar that you see here, and radar is very useful in mines and in dusty environments because it's one of the few sensors that gives us good information when there's high levels of contamination or dust. If you take a laser sensor down to a mine or a camera, it's typically useless within minutes because it's covered in dust, whereas the radar and sometimes thermal imagery can give us good information. The only thing is, we pay a price for that because radar is not always that easy to use. In other words, it gives us a lot of false alarms. In other words, it often says there's something there when there isn't. Sometimes, unfortunately, it misses targets, which is quite dangerous, as well as giving us sometimes good information. Here you can see the result of using that sensor setup where we just put the vehicle stationary and it's outside campus, tracking people and cars as they move around. So the black dots correspond to laser data we're getting. You can sometimes see cars going by, people moving around. The red dots that you see here correspond to radar detections. And if you look carefully, sometimes they disappear when people are going and sometimes they appear again. And that's because sometimes the radar fails to detect them and then detects them again. And the challenge here is to really create an algorithm, a multi-target tracking algorithm, that comes up with these blue squares and the corresponding numbers on them. The blue squares are estimates of the tracks, and they are supposed to stay there even when the radar data disappears. And the numbers are individual track identities. This is not working perfectly. Sometimes when tracks cross, the tracker gets confused and the numbers change, although they shouldn't. But what you can see is the idea is that we're fusing data actually from LiDAR and from radar. We're also injecting some kind of artificial fog from one of those disco fog machines. You can even see it, I think, on the laser data here. And you see then it's then that the radar is able to produce good information and maintain the tracks. So these are the challenges in multi-target tracking, being able to produce probabilistic algorithms that can deal with all the uncertainty of the different sensors. Another application that I've been involved with is environmental sensing or monitoring the environment. This was a project way back in Singapore, which is called the Center for Environmental Sensing and Monitoring, or CENSAM. It was a Singapore-MIT alliance project. A colleague of mine at MIT provided this kayak, and we kind of kitted it out to do various monitoring. The idea is that we're monitoring the salt levels in the sea, the salinity, as well as temperatures, because sometimes there are algae blooms. We have these red tides. So it's important to be able to make measurements in coastal environments. Our part in the project was really to be able to do the navigation so that these ships, these autonomous vehicles, knew where they were at any given time. Now, this is a video that has absolutely no scientific meaning, but I enjoy showing it anyway. It shows an experiment when we were out on the barge. See?
Qué bonitos ojos tienes, bajo de esas dos cejas, bajo de esas dos cejas, qué bonitos ojos tienes. Ellos me quieren mirar, pero si tú no los dejas, ni siquiera parpadear. Malagueña, salerosa. Mis labios quisiera, tus labios quisiera, malagueña salerosa, y decirte, niña hermosa.
So once again, the challenges the process of data, statistical management. Nice music, but I'll advance anyway. Here you can see, for example, a typical path that was made by this kayak near to the coast of Singapore. And what we're doing here is we are superimposing along that path all the detections as black dots that we got from the radar. Now you can see many of them are concentrated at the location of true items. For example, there were known to be items at these red squares, green squares. They correspond to buoys in the water, ships, but there's a lot of false alarms as well. And even the data coming from them is kind of very smeared in angular space. So again, the challenge is to be able to come up with SLAM algorithms that can accurately monitor the path of the vehicle as well as the location of the objects. Here you can see the result of two different SLAM algorithms. One of them is a random set based concept I'll talk about in a few minutes. The important thing is that SLAM is a concept, not an algorithm. There are many SLAM algorithms. Most of them or all of them fail under the right, or maybe I should say the wrong circumstances. So it's important to be able to quantify and really test your algorithms that they work correctly. Okay, so I mentioned lots and lots of examples, probably talked too long, but let's have a little look at this tool that I was talking about. The kind of focus of today's talk is this concept of random finite sets, which have been around for about, well, since 2000, so probably about 25 years now. It's being used in many applications, as I just showed. And let's look at why we're interested in them and what they even are, okay? Here you can see some data recorded from very different sensors. So this is a plan view of a car park, actually done in Singapore many years ago. And the green ellipses, or they should be circles, but they're distorted slightly. Those green circles correspond to the locations of tree trunks, lampposts in the environment. And the red crosses correspond to instantaneous detections made by a radar recorded from the origin here. So the robot was located here. Now, if you look carefully at this, you'll see that many of the red crosses do correspond to the green circles, which is good. So we're getting some useful information. However, some of them are missed. You see things like a tree that was detected here. There's no red crosses near the lampposts over here. And also we're getting these false alarms that are appearing here. In other words, the radar says something is here when in fact it isn't. Now, what we then did is switched on the radar just a couple of minutes later. Nothing changed in the environment at all. And you'll see the random nature of the detection. So here, we're starting to see that the lampposts appear to be detected, albeit with spatial errors, and the false alarms are now different, even though nothing in the environment changed at all. So the important thing is, there are two major forms of uncertainty here. When something is detected, it appears that there's spatial uncertainty. Well, spatial uncertainty we can measure in meters. If there's an error in my range value, then I can quantify that error in meters, for example. But the detection errors, they don't have any units at all. If something is misdetected, I cannot give it units of meters. So therefore, we need paradigms, or we need mathematical tools that can simultaneously deal with both types of uncertainty and allow us to use Bayesian estimation to deal with them. That's what random finite sets were developed for. That's the reason they exist. Similarly, here we're doing RANSAC with laser data. You'll see that occasionally the correct line is detected, sometimes the false one. Here is visual speeded up robust features, or SURF features from vision. If you look carefully at the bottom, the features or the size of the circles detected corresponding to contrast changes is different, even though the scene didn't change. So detections are random in nature in a lot of the work that we do. And that's why we model detections or observations or measurements with something that we call a random, a random set. here you can see a random set of measurements, and this, for example, could contain range and bearing vectors. So it's a set containing range and bearing vectors. This would be the first detection that I got. This would be the second detection that I got. And the important difference between this and random vectors that are used in many state-of-the-art approaches is that the number of elements is itself now a random variable. So when we do random vector approach methods, a vector has to have a fixed size. Now, when you and I make a computer program, we don't even think of vectors and sets. It's an array in the computer. And we can nicely make arrays bigger and smaller. We can chop off bits. But the fact is we need rules or heuristics to do that. And if you're strictly talking about vectors, once you've defined a vector, you cannot change its size. So this actually offers a mathematical way to correctly deal with uncertainty, not only in the values of z's, of z1, z2, for example, at time k, but also in terms of the number. And remember, I showed you that radar scan. So, for example, at one instant in time, we might have a certain number of detections. At another instant in time, that number can change in a random manner. So a random finite set, so that I can define it, is that at any instant in time, we've got this finite set of measurements. For example, I may detect no features, so it would be the empty set. I could detect one feature, and so on. So the number of those detections, if you like, is also part of the random process. That has actually powerful consequences. You might say, we're engineers, let's let the mathematicians lose sleep over that, who cares? But it turns out that if we use random sets with Bayesian-based methods, and when I say Bayesian methods, I mean things like the Kalman filter, particle filters, more modern filters such as Bernoulli filters, we can now actually estimate not only the location of features in my map, but I also estimate the number of them, rather than using a bunch of rules separate from the Bayesian analysis to come up with this number. Another reason why random finite sets are very powerful and very useful can be understood by looking at some very trivial examples. Let's go back to basics. Imagine a 2D world, so a planar world, I'm looking down on it. And imagine there are two pillars or trees located at these green circles. Okay, so for example, one is at the origin, another one is at coordinates 1, 1. So the true map, or the true list of targets, if I'm doing target tracking, corresponds to M, where I've got one target or one feature or one landmark at the origin, and there's another one at coordinates 1, 1. Now imagine I've got a robot moving along this path, and the robot has a computer on board, it's trying to do SLAM, and it makes an estimate of the world it's in, and it detects the feature at coordinates 1, 1 first, and the one at the origin second. So its estimates, so estimates have hats on them, so M hat is the estimate of the world, is 1, 1, 0, 0. Now, if you treat these as random vectors, which is what most state-of-the-art SLAM algorithms would do, or target tracking algorithms, interestingly, if I compare them, I get a non-zero error, even though intuitively my robot has done a perfect job of estimating the world. It just got them in the wrong order compared to my ground truth map. And because of this ordering, I get an error here of 2, which is not 0, even though the robot's done a perfect job at estimating the map. Well, now the first thing you'd probably say to me, yes, but I could rearrange this. I could consider all permutations of M hat and compare those with the ground truth. And there would, of course, be a permutation. In this case, I just simply would swap them because it's a simple example. And then, of course, the error would become 0. Well, interestingly, if you permute the elements of a vector, then mathematically, you're no longer talking about a vector, you're talking about a set. Because a set, by definition, is all permutations of a vector. So when you do that, you're inadvertently, without knowing it maybe, considering sets. Let's look at another example over here. Imagine the same scenario, but this time the feature at the origin for some reason was missed. So the robot's moving along this path, and because of sensor uncertainty, it failed to detect the feature at the origin, and therefore its estimate corresponds to the first feature that it detected, and the ground truth is this. Interestingly, mathematically, if I've got two vectors, m and m hat in the second scenario, you cannot even find the error. It's undefined because they're different cardinalities. Interestingly, if you consider them to be sets, you can find the difference using Hausdorff distance or various metrics which are defined for sets. So that's an important concept as well. Basically, this is another example showing that when you do estimation, and we're in robotics and in multi-target tracking, we're very interested in estimation. Estimation has very little meaning without a very clear concept of the estimation error. Anybody can build an estimator, and here's my estimate. But of course, you need to know how good it is. You've got to look at what the error of your estimate is. And if it's not clear how to define estimation error, then what is the meaning of how to do this? Here's an example of a ground truth map with 3 circles. So this is where features really are. And my estimator says there are 4 features at the black crosses. How do I define the estimation error in this case? Any ideas? Can anybody tell me? How would you find the error in my black map and the green circles? What could you do? Somebody's saying something? Yeah? Don't be shy. Go on. Okay. So what could we do? What could we do with the x? Okay. Well, I'll tell you what's typically done. There are various ways of doing it. Typically, what would be done is we would run now what we call a data association and a map management algorithm. Now, those sound very nice things, but they are in fact totally heuristic. They are basically a set of rules. Even if you use a nearest neighbor algorithm, it has quite a bit of maths associated with it, but it is a heuristic. And what we would say is, well, look, my computer's decided that these are closest together, the ones linked with the red lines, and this appears to be an outlier. Although I could be wrong, of course. It could be that that one belongs to that one, and this happens to be a false alarm. But anyway, it would be sensible to do this. So let's associate these 3, and we'll remove that one. And now, of course, I can now specify the mapping error. I could find the average length of these red lines. That would give me a number. And that number, I could say that is the mapping error. But now look closely. Imagine instead that my estimated map, instead of these 4 black crosses, imagine it was this. Now, look carefully. If I go back, notice that that was a subset of this one. Okay? If I apply exactly the same logic I just said to this new map, I will get exactly the same mapping error, because those are the ones that will still be associated. The rest will be removed, and my mapping error is the same, which is not intuitive at all, because clearly this mapping algorithm is making a lot of mistakes compared to the last one. Again, if we use set-based formulations, we can deal with that. In a nutshell, I don't want to go on and on. I could show a lot more mathematical examples, but I don't want to bore you to tears. But in a nutshell, those of you that might be familiar with Bayesian analysis, all filters, whether it's a Kalman filter, a particle filter, multi-Bernoulli filters, they are all derived and based from Bayes' theorem. And Bayes' theorem says we start off with our prior knowledge about the state X, and we come up with an improved one, given that we integrate a measurement Z. And we run this iteratively. So after we've done it once, this becomes the new prior, and we do it again once we get another measurement. Now, if you use random vectors for the state, it turns out if you change the order of the elements in the state, which effectively means if I associate measurements with different state elements, Bayes' theorem gives me a different estimate. The concept of random finite sets is if I change the order of the elements in my random finite sets, which we call this mathcal x or the squiggly x, Bayes' theorem will always give me exactly the same estimate. So it's a powerful set of mathematical tools which effectively eliminates the need for map management and data association heuristics. That's the reasoning behind it. And so why use random finite sets? Well, we have a specific set algebra that we can make use of. Data association becomes implicit within the Bayesian recursion rather than having to do it separately from Bayesian recursion. and it allows us to consistently or to come up with a good definition of error metrics. And there's been various solutions. As with all engineering methods, similarly with state-of-the-art vector-based methods, we do need approximations to implement them. They become computationally, just like the Kalman filter. If we have thousands of features in an environment, we need to do something in order to be able to make it a manageable problem. The nice thing with the random sets is, well, with vector-based methods, if I had 1,000 features, I would need to come up with my own set of rules to remove some of them. And also, if I have too many measurements, if I have thousands of detections, I would have to remove some of them. I'd say, oh, let's remove these 100 measurements over here, let's remove those, based on some kind of heuristics and rules. With random set methods, the Bayesian process comes up with weights for each feature, and you can then trim very low weights in order to make things computationally manageable. So yes, approximations are still needed, but we would argue they're done in a more principled manner. Okay, let's focus on this SLAM problem. So hopefully I've tried to sell you a little bit why random sets are interesting. One of the difficulties with random sets, the reason it's a new concept, is that to do things like Bayes' theorem, you need to have concepts of a probability density function. That means you've got to be able to differentiate, because it's a kind of a density. Also, you have to have concepts like marginalization. You need to be able to integrate random variables in order to, again, use Bayes' theorem. For vectors, differentiation and integration is clearly defined. For sets, it is not. You cannot integrate sets. You cannot differentiate sets. That's why random finite sets, there's this set of tools called finite set statistics, which are meaningful ways to come up with ways to differentiate and integrate those things and use them within these frameworks. But anyway, I won't go to bore you too much with that. Let's look at some kind of trivial SLAM results and some more up-to-date complicated ones. I'm showing you this one because it shows the concept a little bit. Clearly, this is a toy world, a two-dimensional plane, a simulation actually where we have a green path corresponding to the true trajectory of a vehicle is doing this spiral, and these green circles corresponding to true features. Okay, these days we want everything 3D, but let's look at this because it shows the concept. Now, in red is an estimate of the trajectory based on a vector-based SLAM approach, which is now a bit of an old one now called FAST-SLAM, factorized solution to SLAM. And the red dots, you can just see them, are the estimated location of the features. And if you look at it, it's doing very, very well. In black, we see, it's a bit of a mouthful, Gaussian mixture, probability, hypothesis, density, simultaneous localization and mapping, but who cares? GM, PhD SLAM filter. It's a random set approach, which is coming up with a black trajectory estimate, which is actually underneath that, and these black crosses. Now, both of them are doing very well. Actually, the RFS one did miss one here if you look carefully. But the reason they both work very, very well is that these features or the detections in the environment are very well spaced in relation to the trajectory of the vehicle. Now, let's make the scene a bit more realistic. Let's add some false alarms. And this is clutter. Now, you might say, why am I doing this? This looks unrealistic. Well, this is all the false measurements superimposed over the entire trajectory. And if you think that's unrealistic, let me zip forward and come back. This is real data. This was the result of driving a vehicle around this loop. It goes under the trees here and back with a real radar. And these are detections from a real radar. You and I look at this and we can see, yeah, there's some useful information in there corresponding to parking spaces, trees, and so on, but a lot of false alarms as well. So that's why, let's look at this simulation here, where we've got the same scenario exactly as this one. The features are in the same places, but I'm adding these false measurements. Now what we can see is, let's do the estimation. So in green is the ground truth, and in blue is actually the odometry measurements from this. Here we can now start to see some interesting differences. So the black trajectory is the random set approach, which is closer to ground truth. It's doing a better job. The red one is the random vector approach. Why is the random vector one diverging so quickly? Well, if you look carefully, you can see, for example, here, we're getting, there's a single target there, but the random vector state-of-the-art approach actually thinks there are 1, 2, 3, 4, 5 targets there. Because of all this clutter, because of all the false alarms, it initiates new targets, and we're using heuristics to try to do the data association and monitor how many. The random set approach estimates the number of targets based on entirely on Bayesian, so it's coming up with a much more accurate estimate of the number of targets there. Clearly not perfect, there's a spatial error, but it's at least got the number corresponding to that target correctly. Sometimes there's still one missed. This was missed by the random set approach, but again, the vector method thinks there are 4 targets there. So some results that you rarely see in SLAM is, what you typically see in SLAM is if we want to plot the mapping error, we might isolate or choose particular features, and let's say, what is the error in its location estimate? But it's important also to monitor the number of features that are detected. And because this was a simulation, the green line shows the true number of features which should have entered the field of view of the sensor within a certain time. So after time index about 1,400, all the features have entered the field of view of this robot. So as it moves around, it should have covered all the field of view, if you like, or all the space corresponding to those features. And you can see that with state-of-the-art methods, the number of features estimated becomes hugely overestimated because of this problem of false alarms. So again, this is one of the reasons we're interested in these random set approaches. As I mentioned, this is the reason we did that simulation, is because in reality, we get data that looks like this. Now, this radar data is superimposed onto the true trajectory of the vehicle. And that's why you and I can kind of recognize things. If I superimpose that same data, all of those radar returns, onto the odometry path of the vehicle, in other words, the path that the odometry thinks occurred, this is what that same data looks like. It looks like a complete mess. And of course, the job of SLAM is to unravel that mess and find the true trajectory and the true location of features based on all that data. And again, using different SLAM algorithms, as I mentioned, SLAM is a concept, not an algorithm. So using state-of-the-art vector-based ones, we get certain results, and using a random set one, we're able to deal better with those false alarms and come up with a more accurate estimate of the trajectory and the location of features in the environment as well. Here we can see a real experiment done in Park O'Higgins. That's a park just opposite our university. We remote controlled this vehicle, if you like, to do this figure 8 shape in the park, and then we had a satellite image of the park at the same time. And we did experiments very early in the morning when there's no one around, and experiments at midday when there's a lot of people around. And the idea is that this vehicle is supposed to make, or actually perform SLAM, and it's got a very naive detector. It's using a laser scanner, and it's trying to detect tree trunks. And all it's doing is it's clustering points from a laser sensor together within a certain radius, and if it gets enough of them, it says, okay, this is a tree trunk. So it's developing what it thinks is a map of the environment. It's working, yeah. The trajectory estimate is the blue one. The odometry is the red one, so the odometry is diverging straight away. If you monitor wheel encoders, it gets lost very, very quickly. And the ground truth position of various tree trunks is represented by these kind of black stars here. So it's coming up with estimates of the map that's around it. It was very painstaking for the students to make ground truth map of this, but we went out and painstakingly monitored where trees and things were using a total station, etc. And this is a result of SLAM doing that. Here you can see, once again, as I said, SLAM is a concept, if you like, not an algorithm in itself. So here's 2 different SLAM algorithms performing on that same data. The blue ellipses correspond to estimates of the features, and the larger the ellipse, the more uncertain it is about where they are. And you can see initially they're coming up with quite different estimates of the map. If I wind that a little bit forward, so if I put this maybe, let's go back a bit. you'll see that the vector-based approach seems to diverge quite quickly. And particularly at the corner here, because of these overestimates in its confidence, and actually, again, because it's not using Bayes' theorem to come up with the number of features, we get this divergence, particularly when there's a sharp turn. Whereas again, a random set approach can deal with that and actually come up with much better estimates of what happened. So the true path of this vehicle was the figure 8 shape that you can see that it's supposed to have, it started here, moves around this figure 8 and comes back. Okay, let me play you a video. I can stop talking for a minute. This is a video made by my student for ICRA some years ago. And this is now a new approach where we go more advanced and use Bernoulli filters, which are also Bayesian based, but can be implemented with random sets. He shows simulation here, and I'll show you some real results in a minute.
To our paper, unifying the SLAM back and front ends, a Bayesian approach with random finite sets. This video will demonstrate the 2D simulation results based on the publicly available simulator included with the G2O libraries. The benchmark is the G2O optimizer together with the maximum likelihood
I'm on
data
100% volume,
Against this
it's a bit
benchmark,
quieter.
the proposed hybrid vector set approach will be compared. To demonstrate the compatibility and advantages
He's
of the hybrid
explaining
vector
some
set SLAM approach,
SLAM
these
data
scenarios
sets that are
corresponding to
available
low,
with
medium,
what
and
we call
high
the
odometry
G2O
noise will be
library. This is a
compared.
publicly
First,
available data
a
set
low odometry noise
with
experiment is
SLAM
shown.
algorithms that were available
On
about
the
5
left,
years
you
ago.
can see the HGLMB SLAM algorithm, and the benchmark results are on the right. The red line and points are the ground truth trajectory and landmarks. In gray, the dead reckoning trajectory is shown.
So grey is
Note
the
that
odometry,
under low odometry noise conditions,
blue is
both
ground
algorithms
truth,
yield
no, red
similar
is
SLAM
ground truth,
performances.
and the blue is the estimate. So they're both working well
Next
when there's
is
low
a run
odometry
with
noise.
higher odometry noise, in which data association becomes more difficult. Note that in this case, the benchmark maximum likelihood data association method is unable to find the correct data association. In contrast, the HGLMB SLAM solution has utilized data association hypotheses which are closer to the ground truth, as demonstrated by the superior trajectory estimate. In this third run, odometry noise is again increased.
So the important thing here is that we're able
Divergence
to
of the maximum
back-correct
likelihood data
trajectory
association
errors.
based approach is clear. It is unable to recover from incorrect data association decisions made near the start of the trajectory. In this part of the last run, you can see that the HGLMB trajectory estimate has developed an inconsistency, where the initial part of the trajectory is rotated slightly clockwise, while the last part of the trajectory has rotated in the opposite direction. Now, if we let the algorithm continue, you can see that the HGLMB SLAM is able to make corrections, yielding an overall consistent trajectory estimate. In state-of-the-art methods, this would usually be referred to as a loop closure. Interestingly, however, no explicit loop closure procedure is included into HGLMB SLAM. In contrast, HGLMB SLAM is able to correct past data association hypotheses, yielding trajectory corrections in a manner similar to the familiar loop closure corrections of other methods. Here you can see a bar graph showing the absolute pose error with Umayamada line. These were generated based on...
I'll advance a bit from there. Okay, so the idea is that we showed the concept there. Importantly, as the odometry noise or the uncertainty in the dead reckoning increases, the random set approach can backtrack, deal with trajectory errors. Yeah, I'm nearly finished. And so you might say, well, all of this has been very two-dimensional, looks like toy examples. So what we did a few years ago is we looked at one of the toughest publicly available SLAM data sets that we could get hold of. And I notice here you have a wonderful location with the nets up for doing drone experiments. It was interesting to see the experiments that are going on there. And this is a data set from the ETH called the UROC data set, where they have what they call an easy, medium, and difficult data set. So a drone is kind of remote controlled to move around an environment which has been extensively mapped. And this drone is carrying these sensors, and they use what they call a Vicon tracking system to come up with ground truth. It's something similar to what dancers use. They attach these discs to themselves, and a computer can monitor, a sensor can monitor exactly where they are at a given time. So if we're going to run a SLAM experiment, it's important to have ground truth. Where was this drone as it's being flown around this environment. And this is a particularly tough data set because what happens is the drone undergoes very high accelerations. It's a 3D experiment. It accelerates very quickly, changes directions instantaneously. So the only motion model we can implement is what we call a Brownian motion model. Like a fly, you don't know what it's going to do next. So we say that we predict the next position to be the same as the previous one, plus noise. That's about all we can do. And now we're using orb features, which are the blue circles here, to actually be able to, as measurements, to do 3D SLAM using this method. Now, the gray dashed line is the ground truth location of the drone from the Vicon system, and the colored trajectory is the estimated one. The darker blue it is, there's less error, and the more red, the higher the error in the estimate. So here you can see, for example, it's diverging quite far, but you see that it suddenly backtracks. So if I rewind that little bit, it's diverging quite far because it's not getting enough features, and suddenly it was able to correct the entire history of the trajectory. So it's using a combination of the random set approach as well as publicly available libraries that you can use for individual SLAM, if you like, using batch-based approaches, the more modern graph-based SLAM approaches. And here you can see, even with the toughest data set, we were actually able to come up with performances which are outperforming Orb SLAM 3, which is the best competitor we could find at that time. And it's doing a pretty good job of estimating the trajectory. Often we get not enough features. Sometimes there's texture like carpet, where we get a lot of orb features which are kind of meaningless because they don't associate across frames. So it's quite important, it's quite useful to be able to just use a single camera, as we're using here, with an orb feature detector to actually come up with estimates of the trajectory. It's still running, but it's been doing a lot of things that are close together. Here you can see kind of the orb features we're getting from a carpet, which are just very difficult to deal with. You just certainly have many false alarms, misdetections in here. Here we can see comparisons with state-of-the-art methods. So Orb SLAM 3 in green and our approach in blue. Typically lower errors. In the most difficult data set, in one of them, the toughest one we could find, ours failed after a certain time. Orb SLAM 3 kept going, but with huge errors. So if you see the magnitude of the error, it's the absolute pose error, is what this metric is called. It starts off already with much larger errors in position and is basically diverging, although it's coming out with estimates. So basically, that's it. So thanks for the warning about the time. In my opinion, then, what is the future in estimation and SLAM and multi-target tracking? If you look at state-of-the-art random vector SLAM methods, they typically deal with detection uncertainty using heuristic methods, and they're only concerned with spatial uncertainty. So they use Gaussians to represent uncertainty, or particles, or various ways, graph-based methods now, which deal with Gaussian-based uncertainty. That requires the external application of measurement to feature track association measurements. And that's what makes them extremely fragile when you have a lot of false data, such as you get in mines, even with the drone experiment you just saw with visual features. As soon as you start getting significant false alarms, misdetections, they typically fail because of what they call the SLAM front-end errors. They typically have a SLAM back-end, which is the math, the algorithm, and the front-end does all the heuristics. The idea of RFS SLAM is that there is no more front-end. The back-end and the front-end are combined. There's no longer a SLAM front-end, and Bayes' theorem takes care of the whole lot, the data association, estimating feature number, and so on. So with that, I think I've been talking for an hour. I'd like to thank all the members of my teams. These are a bit outdated, these photos, but never mind. Various people that have made all these results possible. And I'd like to thank you for your time as well. If you have any questions, I'd try my best to answer them.
Agora a gente vai estar aberto para perguntas e fiquem à vontade de fazer as perguntas tanto em português quanto em inglês.
Good morning. First of all, thank you for the speech. It was really, really interesting. I would like to know, how can these methods be used in the context of astrobodies detection, such as exoplanets and its algorithms for recognition?
Okay, yeah, thanks. Yeah, that's a good question. So I think you're asking how can it be used in combination with more modern machine learning methods, for example? Yeah, that's a good question. So, well, actually, many of my students, when I try to get them to come and do PhD or a master's with me, I talk about these concepts because I'm getting old, I guess. And they all come and they just start using machine learning methods, neural networks, and so faster RCNN. But actually, we find that they combine very, very well. So, for example, to do the people detection, the actual detection itself, many of my students use faster RCNN, or you can go and use YOLO, you only look once. There's all these things available online, which are based on machine learning based methods. So we don't really compete with them, we're actually using them. But of course, those methods too, occasionally, they still produce false alarms. Sometimes they fail to detect something. So we need some kind of smoothing concept that fills in the gaps. And I guess that's where this all comes together. So it's not really that it's completely competing against it. It's actually, I think the two can work quite well together.
And I have another question in this aspect of false alarms and error detections, because in the space cases, there could be lots of anomalous activities because it's a field that we don't have the certainty of much of the things. So how can these filters and all this, it is actually an error or whether it is an anomalous activity?
Yeah, okay, no, that's a good question too. Yeah, so, well, so these methods, we typically, they use models of motion, and they use models for measurements, how the measurements relate to the state. And many of the arguments put forward in the machine learning method is we don't want models anymore, we don't use that. But actually, when you think about it, if you really go deep down into these things, the example I just showed you with the drone, technically you can say it's a model, but the model can encompass anything, is Brownian motion. That means that you have no idea how the thing's going to move. And we just say that the next location we're going to predict is the same as the previous one with noise. And that's how you perhaps model a fly going around the room, things like that. Now, when you say about many things happening that are perhaps nothing to do with what you want to estimate or track or detect, of course, all of these concepts, they break down eventually. And I think the whole point of research is we test any new ideas we have until they break. And you hopefully try to show that they break later or less often than state of the art. That's the whole point of research, in my opinion. So yes, it's very difficult to come up with something that can cover all activities. But I think, like you say, if there's, by considering false data, false alarms, misdetections, is probably some of the best things we can do in a situation like you're talking about. Unless you can really have some kind of models, and those models can be learned. You can use deep learning approaches to learn functions that can still be used with these concepts. So it's not that we're excluding learning. You can even use it within these concepts to do the same kind of things. But at the end of the day, everything breaks under the right or the wrong circumstances.
Thank you.
Okay, thank you.
Hello. How does the random finite sets approach compares with the random vector approach in terms of computational complexity?
Yeah, that's a very good question. Yeah. So, okay, well, both run into computational complexity problems. If you use state-of-the-art Kalman filter from years ago, if you use the more modern GT-SAM graph-based approaches, as soon as you have thousands, even millions of detections, and you start getting thousands, even millions of state estimates, they become intractable. So something that I did mention in there, the same applies to random set approaches. It's not a perfect solution by any means. If you try to implement them in their entirety, you'll very soon run into computational issues. The thing that is fundamentally different with the random set approach is a term that I didn't show here because I didn't want to bore everybody with the maths, is something called the measurement likelihood function. Now, when you do SLAM, you combine the likelihood of a measurement with the prior estimate to get a new one. Now, the measurement likelihood in state-of-the-art methods that you're talking about has a lot of heuristics associated with it. Because, for example, if you detect 5 features, but your state only has 4 in it, to get that measurement likelihood, you've got to throw one of your measurements out using a rule, or they call them map management algorithms, is a fancy way of saying a rule, which is what it is. To be honest, a rule is a bit of a dirty word in engineering and the reason it is because unfortunately they often fail and make things fragile. Now, with the random set approach, you form the measurement likelihood by combining every single measurement with every single possible estimate, which becomes computationally intractable quite soon. But what you can do is you can do all of that within the Bayesian framework, and it comes up with all of these filters, come up with weights for your individual components. So, for example, a filter which is called the multi-Bernoulli filter comes up with weights for every component that forms your new solution. And you can then start eliminating those by trimming low weight costs. Now, it's an approximation, of course. You don't have the full posterior, just like you would approximate state-of-the-art methods by cutting out measurements, cutting out state values. But we argue that it's more principled because Bayes' theorem is still giving you the full picture and you're simply cutting by weights. And those weights are formed through the Bayesian algorithm. That's the kind of fundamental difference. So I guess it comes down to the philosophy, do you want to make approximations and then use a principled approach? In other words, you do map management and then use Bayes' theorem? Or do you use Bayes' theorem, a principled approach in our opinion, and then start making the approximations? We believe the second one is the right way to go. But of course, there are approximations to get things working. Yeah.
Okay, thank you.
Okay, thank you.
Okay, I had 3 questions. The first one about this different kind of the finite sets approach. What would be a good start point for studying this technique?
That's a very good question. Yeah. Well, this was all started by the person is called Ronald Mahler. He's retired now. He worked for Lockheed Martin in the United States. He came up with 2 books called Information Fusion. And he came up with what he calls Finite Set Statistics 101. Now, his 2 books are that thick, and I guess it's like the Bible of this stuff, and horrible to read because he's a mathematician. So we, as engineers, try to interpret the parts that we need. We do always refer back to that book. But yeah, a good way, I think, to get into it is to look at, well, if you're interested in robotics, we're the ones that have tried to implement that in robotics. There are other groups as well. There's a group in Lund University, they're using random sets. There's a group in Italy, Battistelli and so on, they've also used random sets. So we are very much trying to apply it. And if you look in some of the spectrum, I can point you, if you're particularly interested, by all means, send me an email. I can send you things that will introduce you to the concepts in robotics. In multi-target tracking is where it's also used a lot. There's other papers I can guide you to as well. I haven't seen it yet in lecture courses. Maybe it's still too new. It took a long time for neural networks and machine learning methods to be introduced into lecture courses. But set theory, unfortunately, is something that the mathematicians tend to do rather than the engineers. Again, the reasons being you can't integrate sets, you can't differentiate them. And that's why we need these nasty looking tools. When you first look at the notation, it's horrible. But when you start to pull them apart, something that I find with estimation theory that's quite nice is, despite horrible notation, once you start to implement something, you actually see that it's implementing something which makes common sense. Even a Kalman filter, the way it combines information, if you look at the uncertainties in one, and if they're equal uncertainties, it just takes the average, and that makes sense. So once you start implementing something, and The nice thing now is you have ROS. So on ROS 2, you have PhD filter, which is one of these. You have a GLMB filter, which is here. There's people in Liverpool, a good colleague of mine in Australia, in Perth. They put a lot of this stuff available as MATLAB functions, also in ROS. You can just use them, start to kind of understand them, maybe make small changes yourself. And that's probably the best way to get, I think, into this stuff, because if you start reading the books, it takes time. It's nasty.
Yeah, and about the techniques, from what I understood, you use Bayesian inference for solving the whole filter. And you said that some of the functions are not differentiable or not integrable. So you need probably you have your inference null unless a constant. So you need some algorithm, some technique, like some Monte Carlo Markov chains or some ways for implementing. Just out of curiosity, what techniques do you use for actually implementing the Bayesian inference?
Yes. Yeah, good question as well. So, so basically, the important thing is everything I've talked about is Bayesian. We derive all of these filters through Bayes' theorem. All goes through, just like the Kalman filter was, the particle filter was, they all go through Bayes' theorem. And you also have something called Bayes optimality. That's something that's important to look at as well. As soon as you start wanting to use sets, the difference between a set and a vector is very basic and very fundamental. If I give you the vector with elements 1, 2, and I give you another vector with the elements the other way around, 2, 1, they're different vectors. But if I give you the set with elements 1, 2, and the set with elements 2, 1, they're the same sets. And what that means is once you do Bayes' theorem, symmetry has to be obeyed. That means if I change the order in that set, it should have no effects at all on the result. And that's what these tools are all geared up to do. And now you asked then about how we implement them. You can do particle filtering with sets. That becomes pretty computationally expensive, just as it does with vectors. I showed with the orbit tracking, I showed an example with particles at first. And the nice thing about particles is they can nicely follow an orbit, whereas a Gaussian just exists in a plane and soon becomes a bad approximation. Particles are expensive, so then it's nice to be able to sometimes change geometry. We had to change to a curvilinear or Riemannian manifold so that you can get a banana-shaped Gaussian. And the nice thing about that is you represent it with only two numbers, the mean and the variance, but it's still nicely banana-shaped because you're now not doing Cartesian anymore. Those are things you can do. The most recent filters, the ones we talked about with the drone, are what we call multi-Bernoulli filters. A Bernoulli filter is quite a nice thing because it needs sets and it comes up with two values. It comes up with a probability of existence of the state and also its spatial estimate. And they're both random variables. So it's estimating the probability that the state is this value, and it gives you its spatial uncertainty. And it has many components. And that number of components very soon becomes intractable. That's why I said then you get these weights, and you have to cut them off. So that's how the modern ones are implemented. But the first one was called the PhD filter, where we actually estimate a map with a function. And the function's quite clever. It's called an intensity function. The maxima of the function correspond to locations of features. And if you integrate the function, it gives you the number of features. So any function you can think of that has maxima corresponding to locations, spatial estimates, and when you integrate it, gives you the number, then you can use that. And the easiest example of such a function would be a sum of Gaussians. Because if you integrate a Gaussian, it's 1. If you integrate a sum of them, it's the number of the features. So, but if you want more information, I can certainly talk to you.
Yes, thank you.
Okay.
Good questions. We'll need to finalize right now because there's not enough time, but thanks for answer. There were really good answers, explanations. I'm really thankful.
Oh, thanks for the interesting questions. It's good.
Agora, antes de finalizar, vamos fazer um sorteio e vai ser sorteio